outside of the drama within your guys' class.
What about other classes?
That's the case everywhere.
Better than middle school.
What?
There's less drama than middle school, but
There's still drama.
yeah. But the drama now is just really drama.
Intense drama. Hey, you know what fixes all drama? Agape love.
Stay away.
Mr. Kramer, like everybody's like drama, drama, drama. I'm like, what drama? I'm literally.
You live under a rock, huh?
Yes.
I'm kidding.
What is drama?
It's drama is
Alright.
drama. No, I know what drama is.
Anything else I missed there? Yeah, he gave you your vocab sheet, so you guys know the drill on doing vocabulary for extra credit. Okay? Yes, sir.
Will this be 2 or 3 points?
Alright. So, let's continue on. We are going to talk about the third temperature scale today. Which scale did we not talk about yesterday? The Kelvin scale. Finally get this in your notes. I will be right back.
Sorry.
Just wanted to.
Did you say you had like 2 pages on your notes?
Yeah.
I ran out of that.
I ran
I'll
out like
give you
last
some of
week.
mine. I
I'm
still
still
have
on
half
the
a
same
notebook.
I'm
How do you
like
know?
back to back.
I have like
I made it all the way to the back, then I flipped it upside down. So
No, I just go front and back on all of these, and I've got this is
I
my
know.
third notebook this year.
I can't do front and back because the thing where you have to write with the bar, the thing.
Oh yeah, I don't have that.
So I just flipped it upside down. I was like,
Sucks to be right-handed.
well, what about if you're writing like on this file and you're left-handed?
I don't have any answers.
So scientists started figuring out that there were some interesting properties of things when they were really, really cold. So they started to figure out, okay, what is the coldest temperature possible? Is there, can you just continue to get colder and colder and colder forever? Or is there a point where you cannot get an object to cool down anymore? What was the vocab word from a different chapter that we said was very much related to temperature? No, good guess. It was in your definition of temperature yesterday. Kinetic energy. Okay? We said the kinetic energy, or the movement of a particle, determines how hot or how cold something is, how high or how low the temperature is. You guys with me? I feel like you're not with me. Okay? So how hot something is has a lot to do with how fast the particle is moving. And how cold something is has to do with how slowly it's moving. So, do you think there's a point at which an object would, or a particle would stop moving? In theory, yes. Right? Now, believe it or not, absolute zero is the theoretical coldest temperature possible, which could you get any colder than stopped? Right? If temperature is based on how fast you're moving, you can't get any slower than stopped, can you? Does that make sense? You can't get any slower than not moving at all. Okay? So in theory, the coldest temperature something could ever achieve would be when that particle ceases to move. Now, what's interesting is absolute zero is what they would call 0 Kelvin. It's on the Kelvin scale. We can convert that to Celsius and figure out what that temperature would be equivalent to in Celsius. Okay. Yep, negative 273.15. However, okay, they've never actually reached absolute zero. So they've gotten to like 0.000000001 degree Kelvin, but haven't been able to actually get to 0 degree Kelvin. For whatever reason, they cannot get a particle to stop completely. It's interesting. I don't know if it's just not possible, or we have not been able to do it, or you can't remove energy away from something that's right next to having no energy because it always goes from hot to cold. I don't know exactly what the reason is, but they've never been able to actually stop a particle completely. I don't know if it creates a black hole or what. Okay? But in theory, the coldest temperature possible is 0 Kelvin. And that's when particles' motion ceases to what? Move. Okay? And maybe you want to write that next to absolute zero. Yes, it is the coldest temperature possible. Okay? But we know that the temperature is based upon how much it's moving. So you can put absolute zero is where particle motion stops. Okay, you very well could see that on a quiz or a test. Okay. Now, there's a couple interesting fiducial points in the Kelvin scale. And they actually use one of the fiducial points as the triple point of water, which I know at this point, you don't know what the triple point of water is. I'll give you the next slide, which will explain it, and then I'll give you a YouTube video which will show you it. I don't have the capacity or the ability to cause an object to boil, melt, freeze, condense, all at one time. I don't have a vacuum. There you go. Put this in, and I'm going to show you a little YouTube video that, believe it or not, shows water freezing at the same time it is boiling. You think that was possible? Either until I start studying it. Basically, the triple point of water is when you have all three phases at once. And they're simultaneously going back and forth between each other. Solid is melting, solid is freezing, solid is boiling, solid is condensing. Or not solid, water. So it says the triple point of water is 273.16 Kelvin. Let's just do some quick review. Can we convert that to Celsius? Okay? Let's do that. So this temperature in Celsius would be 273.16 minus 273. Your temperature in Celsius would be what? 0.16 degrees Celsius. Could we take that and convert that to Fahrenheit? Anybody got that equation for me? What is it? PF 1.8 PC plus or minus 32, I can't remember. Okay? Let's figure out what this temperature would be in Fahrenheit. Somebody plug that into their calculator. It's going to be a little bit over 32 degrees Fahrenheit, but let's just tell me what exactly it is. 32.288 degrees Fahrenheit. All right. Is it possible that in any given time we have been at 32 degrees Fahrenheit before? Does that mean at 32 degrees Fahrenheit we're going to see water turn from a solid to a liquid to a gas, from a gas back to a liquid to a solid all at once? And the answer is no, and here's why. It is when the temperature and pressure are such. Okay? We can't really affect the atmospheric pressure much, can we? Okay? Can I change it just by, swinging my arms and sucking in air? Is that really going to change the atmospheric pressure very much? No. Okay? How they achieve this is actually use a vacuum to change the pressure. Okay? So you're not going to be walking down the street and all of a sudden seeing a body of water like a lake. You're not going to see it freeze while it's boiling, while it's condensing, while it's melting all at one time. You won't see that. Okay? Because it has to be under specific pressure conditions. Okay? You'd only be able to do it with the right apparatuses and right techniques. So I'm going to show you a YouTube video where they do it. And it's pretty cool because you get to see it freeze while it's boiling. Tell me that's not cool. You guys don't think that's cool? You guys don't seem very excited about that. It's like not something you see on an everyday basis. It's freezing over and bubbling at the same time. You not want me even to show it? Are you sure you want me to show it? You don't seem too interested in seeing it. Okay, all right. Audrey, can you turn off the lights? Or, yeah, turn off. I turned it off because I don't know. I don't remember if there was like someone's language or anything like that. So just to protect us from thinking, wow, that's really cool, Mr. Kramer.
That's really cool.
Okay, well, that's just boiling. Nothing's happening yet. Hold on, let me see. 3 seconds after. 2 minutes later, triple point occurs. Okay. It's really touchy. It's not easy to get at that triple point. Because we do know temperature, pressure, and volume are all related to each other. And so it's very difficult. So what's it doing right now? Freezing. It's freezing, okay? Now what's it doing?
It's one world.
Okay? Eventually you cannot maintain this because it's very difficult to maintain the perfect temperature and the perfect pressure over a period of time. Eventually you won't see both happening anymore. But was there definitely bubbles happening? Okay, there was boiling happening. Okay? To be able to maintain that's almost impossible. Okay? But for a short period of time you can get all of them to happen. Now, are you going to be able to see the condensation? Probably not very well. Are you going to be able to see the gas particles moving around? You're probably not going to be able to see that. So you're only able to see some of the effects of it. Okay? So the effects of of like would be like bubbles and seeing it freeze. Okay? But that's pretty cool. And if you take advanced chemistry, you will find out that actually melting and freezing happens through the gas phase. Alright. Now, this you've already gotten, so you need me to put it up there. You're probably thinking, well, what about the 0.15? Well, 0.15 you don't need to worry about. It's such a minute difference that I don't even use it. So you can just do 273. Cool? Okay, so we're not going to do the 0.15. You don't need to write this down. Okay, don't you already have it? Well, if you want to write it down in this chapter, you certainly can, because I think it was last chapter that I gave it to you. So you certainly could, but you don't have to put the 0.15 on there. Just the temperature plus 273, the temperature minus 273. And it doesn't say TK, so if you want to put the K with the big T, you can do that. What was that?
But I like the 1.5.
Yeah, it's more precise, I know, it is. But a 0.15 difference on the Kelvin scale is very small.
Because that would make water 0.0101.
Yes, which is what it actually is. But okay. All right. We did talk a little bit about this yesterday, but I do want you to get in your notes. We said that temperature has an effect on a lot of the properties of matter, and I specifically talked about expansion, thermal expansion. I'm going to show you a couple demonstrations too here of things expanding. I think it was this class. Did I talk about the bridges in this class? Anybody else think of, I could be drawing a blank on some things, think of something that you've seen where they've had grooves or cracks or something to help protect from something expanding and causing something to break or collapse. Anybody think of anything that I may have missed? It's possible that you guys come up with something. If not, it's no big deal. But okay. Buildings, okay. Usually buildings. Oh, I can give you actually a pretty cool example. So I don't know if anybody has ever seen someone hang a door. You know what I mean when I say hang a door? Put a door in, essentially. Okay. So when I finished my basement, I had to put in 3 different doors, and it was during the winter time. And in the wintertime, I usually have my wood-burning stove in the basement, like, kind of blaring, you know? And so I found that I must have been doing it either when it was really hot or the opposite, I don't remember. But like sometimes my door will shut and open really easily, and other times my door won't even shut because of the temperature difference in the summer versus the winter, and whether or not I have the wood-burning stove on or not, because the foundation and the walls and the door will start to expand or not, which will change whether or not I can open my door, which is kind of cool. But you guys probably don't experience that often because, you know, I'm probably not a great door hanger in the first place. I probably didn't do it perfectly. That doesn't probably help, but definitely it doesn't make a whole lot of sense unless you understand thermal expansion, why I'd be able to close and open the door fine one day and then not even be able to do it the next day, and then 2 days later be able to do it just fine. It has to do with things expand due to changes in heat. Okay? Before I give you a demonstration, I'm going to have you put this in. Some things expand more than others when they when you increase the temperature. And this gives you a couple examples. The brass expands a lot when you heat it up. Okay? We could also talk about different phases expand differently. So do you think they had to understand the thermal expansion properties of the fluid they put in thermometers? Right, if they didn't understand how the fluid in that thermometer expanded, do you think they were going to be able to correctly do a thermometer to measure temperature correctly? Like, no, we're not going to be able to. Okay? So when you guys done, come on over here. I'll show you a couple little demonstration of things in thermal expansion. You can probably imagine what's going to happen here, but pretty cool either way. Wait for Shane. Exhibit A. Right, you probably can imagine what's going to happen, but okay. A little bit. Anybody want to be branded? No. I can maybe like get this lip. Ouch. Don't laugh too hard. Alright, let's see. Alright. Is this what? Want me to do it again?
Yes.
This isn't magic, guys. It literally is expanding. You just can't probably see it very well. I'm not pulling the wool over your eyes with a magic trick here. Yeah, hopefully I got all that water off. That's not going through. Ooh! Okay, how much did it expand enough? I'm glad it didn't burn me. That could have been bad. I was pushing pretty hard. Okay, yeah, I'm not gonna push too hard, just cause.
You're very close to it.
No big deal. Okay, I'm gonna use this little thing here. Pretty simple, right? Just metal, right?
Whoa.
Bending.
Oh.
Whoa, wait, what? Oh, what the? Wait.
I can cut through butter right now. I'm gonna shut this off so I can hear myself.
Whoa. What is
That is so weird.
Sneaky, sneaky. Have a seat. I'll explain why this did what it did.
Whoa.
Probably separate seats.
In real life.
Okay, I don't know if you noticed anything, but do you see the color difference to both sides? At least on the bottom, this is kind of more of a copper looking, and this is different.
Yeah.
The reason why this did what it did is because this is not the same metal. One side is one kind of metal, and the other side is another kind of metal. And what does this slide just tell you?
Brass.
Some things expand more than others. So if one side is one metal, and another side is a different material, is it possible that one of the sides could have expanded more than the other? Which would have caused it to what? Bend. Okay? And as soon as I put it under the water and cooled it back down, it went back to its original state, and that's why it looks straight. Okay? So a couple cool little neat examples of thermal expansion. Okay? Could there be purposes where you might want to use like different materials and maybe cause something to bend based on, you know, heating it up or not? Is there probably some applications for that? Okay? I can't think of any off the top of my head, but yes, I'm sure there are some applications of that. So let's keep going here. Other things that happen when you heat something up. Does anybody know what a conductor is? Don't say train driver. Don't say choir director. Yep, something that allows electricity to flow through really well. Okay, can you think of anything that may allow electricity to flow really well through it? Some examples. Wires, yes, that makes sense, right? When you plug in your appliance into an outlet, that is usually connected by a what?
Why?
By a wire, okay? And you would want some material to allow electricity to flow through it, hence why you would use a conducting material. Okay, water's a very good conductor. That's why you don't want to be swimming in a thunderstorm. Because all that current can go into the water and through your body and zap you. Okay? Not good. That's why if you're an electrician, you don't really want to be working with wires when you're sweating.
Ow.
Because, yeah, you could potentially zap yourself pretty good if you touched the wrong thing. With, you know, it'd be more dangerous if you were sweaty than if you were not. Okay? Now, it does say that there's a thing called resistance, and you will learn more about this when you take physics, but every material has a certain amount of resistance to it. Basically, what resistance is it resists the ability for electricity to flow through it. Okay? Wires have low resistance. Okay? But part of the reason why light bulbs are bright and give off heat is because they're a very resistive material. So when electricity goes through it, there's a ton of friction. Well, what do we know friction does? Causes things to heat up, right? Okay? So when you touch a light bulb, the reason why it's hot is because electricity is flowing through it and it's getting resisted a lot, causing a lot of friction, and that's why energy gets dissipated in the form of light and heat. Okay? However, if you increase the temperature, it will increase the electrical resistance. Okay, so if you wanted something to resist current more, you could just increase the temperature. However, you got to be careful with that. Okay, I could go into all the little details as to why, but it probably won't make a ton of sense to you at this point since you don't know much about the things that go into electricity. Last slide, I think. Viscosity, we have talked about that, right? We didn't talk about that in the fluid chapter, did we? Which chapter did we talk about viscosity?
It was like the changes in matter.
Oh, okay, that makes sense. We have talked about this, right?
Yeah.
For sure. Sometimes I don't remember which class I talked about what because they do kind of overlap a little bit. Like go, like, we'll talk about a lot of the same things in other classes, but we'll just go deeper and more advanced into them. Sometimes I don't know which class I talked about something is. So yeah, first bullet is your definition of viscosity. Okay, I gave another like layman's term definition, I think, before. I just said like how thick a liquid is. While the correct definition is a fluid's ability to resist flowing. So give me some materials, I think I asked you this before, some materials that are really viscous or don't flow very well. Syrup doesn't flow very well. Honey doesn't flow very well, does it? Right? Scabs on your lip don't flow very well.
You were always standing over here and
A student said, why do you have hair coming out of your lip?
oh my.
I said, no, that is...
Got me in there, but
No.
no.
So these classes are actually mine from second grade, so I can't really see all of them
Terrible.
because my prescription is changed. So it literally just looks like black food.
Hi, hey, let me finish this. I do want to explain this. Has anybody ever took syrup, put it in the microwave, heat it up?
No.
What does it do when you heat it up?
It's more runny.
It's more runny, or you could say it flows better, right? So if you increase the temperature of something, is it become more viscous or less viscous? Less viscous, because it flows more. Okay?
Why would you put syrup?
Why would you want cold syrup on your pancakes?
Because it's like more
I dip my pancakes in syrup. People dip pancakes.
It's called pancakes. Yeah, but you want a little bit.
Why not just have butter? Have nice
Because syrup and butter's better.
syrup sucks because I don't
You
like
suck.
anything.
Easy.
Syrup's amazing.
Who's on the board? You. Me? What's up?
Dang it, Steve. We just stuck here again.
Yeah, I know. I'm so irresponsible.
What are we doing?
I thought about it. Are you?
Mr. Kramer, putting the sign.
Yeah, I'll stay.
I was just walking down the hallway. It's like, oh, I wonder what's for lunch today.